Welcome to the lecture about models and evaluation. In this video, we will focus on the training part of the machine learning cycle as well as the evaluation part. A machine learning model can be described as a relationship between output or response variables and its corresponding input or dependent variables in a dataset. This relationship can be expressed via a mathematical equation, function, or rule. The idea is not to predict a correct output for every input, but to generalize well over lots of data points, such that the error is minimum and the same is maintained when you use this model over new data points. Here is the workflow for model building, in this case for a linear regression, which is used as the algorithm for learning. In the next slide, we will review a number of machine learning algorithms for model building. Remember that machine learning methods can be classified based on the level of supervision they require, like supervised learning, unsupervised learning, or reinforcement learning were the three types we review in the first lecture. The algorithms that you can use really depends on the type of learning that you're doing. You can use, for example, for supervised learning, regression and classification, whereas for unsupervised, clustering methods or association methods are appropriate for building your models. So let's focus now on regression models or algorithms to help create models. The input data is generally labeled with continuous numerical values instead of discrete ones. There are three major categories of regression models: simple linear regression, a multilinear regression, and non-linear regression. And we have here depicted a sample graph and their sample equations. Let's start with simple linear regression. It shows the linear relationship between the independent variable in the x-axis, which is experience in this case, and the dependent variable, which is the y shown in the y-axis here, which is salary. It is called simple because there is only one input variable, x, and it shows this linear relation. Typical application for this kind of algorithm is a trend analysis and forecasting and prediction. Multiple linear regression is a generalized form of simple linear regression that uses several independent variables to predict the dependent variable. In this case, in the graph here, this is the body mass index versus the calorie intake, but taking into consideration factors or risk factors in this case as gender and physical activity. In this case, Y is the continuous measurement outcome, the body mass index. B0 in the formula is the y-intercept or starting value. That is the value of y when all other parameters are set to 0. x1, x2, xn are the values of independent predictor variables, like in our case are risk factors. And b1, b2, b3, bn are the values of the coefficients for those risk factors, or in this case, independent predictors. Last, nonlinear regression is a general technique that adjusts a curve instead of a line of linear regression for a given dataset. In this example, we have this quadratic function that adjusts well to this point, data points. The nonlinear regression algorithm aims to capture complex patterns and interactions that cannot be effectively represented by a linear mode. A nonlinear relationship means that the change in the dependent variable is not proportional. Examples of these are drug response curves, enzyme kinetic curves, and so on. This is an example of a quadratic polynomial curve in this case. Other type of task we can perform doing supervised learning is classification. The output there is normally a label or category to which the input data point may belong. It involves a training set of data in which we have the data points labeled with their correct classes or categories. There are a number of classification tasks with different objectives. For example, we have some tasks like binary classification. In this particular example, we are trying to decide whether an email is a spam or not spam. Multi-class classification means that we want to classify, in this case, an image of an animal into its appropriate class, where there are more than 2 classes. And multi-level classification means that we can classify this particular image into 2 or more categories. Typical classification models are listed here, and those that are underlined are the ones that we will review in the next slides. Logistic regression uses sigmoid function or logistic function to model the data. It is a predictive analysis algorithm which works on a concept of probability. Given a set of observations, logistic regression algorithms help us to classify these observations into 2 or more discrete classes. So the target variable is discrete in nature. Normally it follows this S-shaped curve, and it uses the concept of threshold levels. Values above the threshold level, or also known as decision boundary, are rounded up to 1, and those below are rounded up to 0. Usually the boundary is set to 0.5. Types of logistic regression include binary, either 0 or 1, pass-fail, true-false, multinomial logistic regression. In this case, the target variable has 3 or more categories which are not in a particular order, so these are nominal categories. An example here would be similar to the example before, where we have many animals and we're trying to categorize one image into any of these categories. Ordinal logistic regression. In this case, the target variable has 3 or more ordinal categories. So there's intrinsic order involved in these categories. For example, if we are talking about price, whether it's low, medium, or high, a support vector machine is a powerful supervised learning algorithm used for classification and also regression. It works by finding the optimal hyperplane, which is a decision boundary, depicted here by this solid black line, that best separates data points of different classes in a feature space. In this case, the 2 classes are the green dots versus the blue diamonds. The margin is the distance between the hyperplane and the closest data points that belongs to each class. Support vector machine, or SVM, aims to maximize this margin, making the classifier more robust and better at generalizing to unseen data. The support vectors are the data points that lie closest to the hyperplane. These points are critical because they define the position and orientation of the hyperplane. If these points were removed, the hyperplane would change. A decision tree can be used for regression as well as classification problems. It works for both categorical and numerical data. It works by learning simple decision rules inferred from the features of the data to predict an output. The model is structured like a tree, as we see in this example, starting from a root node, which represents the entire data set. At each internal node, the data is split based on the feature that results in the best separation according to some criteria. Each branch represents the outcome of the decision or test on a feature. And each leaf node, which are the terminal nodes, represents a final prediction or class label. The process of splitting continues recursively, choosing features that best divide the data until certain stopping conditions are met. The goal of the decision tree is partition the data in such a way that each leaf node contains instances that are as similar or pure as possible. The tree learns to make decisions by asking a series of yes or no questions. and moving down the tree until it reaches a conclusion. So if we have an example here that we're trying to predict if people will die at a younger age or older age, assuming that younger is younger than 70, the characteristics like being a drinker, smoker, or overweight will act as a predictor value. Using this, we can consider age as a response variable, and this decision tree explains that if a person is a smoker, they will die young. If a person is not a smoker, then the next factor to consider is if the person is a drinker. If a person is not a smoker and not a drinker, they're gonna die old. If a person is not a smoker and is a drinker, then the weight of the person is considered. If the person is not a smoker, not a drinker, but is overweight, then the person, depending on the overweight, talking about higher than 90, the outcome is that is predicted to die young. A random forest is an ensemble learning method that combines many decision trees to improve prediction accuracy and control over fitting. It's used both for classification and regression tasks. The core idea is to build a forest of decision trees, each trained on a random subset of the data. This technique is called bootstrap sampling or bagging. Additionally, when building each tree, a random subset of features is considered at each split rather than all features. These add more diversity among the trees and reduce correlation between them. So when making predictions for classification tasks, each tree votes for a class and the majority vote is the final prediction. In the case of regression, the final output is typically the average of all the tree predictions. In the case of unsupervised learning, we don't have pre-labeled data to train and build our model. So we can use clustering models, which is clustering is a process of grouping similar data points together that do not have any pre-labeled class or categories. The output would be a segregated group of data points. We will review 3 types of clustering algorithm: partition-based clustering, hierarchical clustering, and density-based clustering. Partition-based clustering is an unsupervised learning method where the goal is to divide the dataset into a fixed number of non-overlapping groups or clusters, such that the data points within each cluster are similar to each other and different from those in the other clusters. The most well-known algorithm in this category is k-mean clustering. In k-means, the user chooses the number of clusters, k, beforehand. In this case would be 4 clusters. The algorithm then will randomly initialize k-cluster centroids, which are the center of each cluster, and assign each data point to the nearest centroid, forming these clusters. Then recalculates each centroid as the mean of all the points in the cluster and will repeat this step until convergence. The objective is to minimize within cluster sum of squares. In other words, to make points within each cluster as close as possible to their centroid. In the case of hierarchical clustering, it can be used as an alternative for the partition-based clustering, as there is no requirement for specifying the number of clusters to be created. The dataset is divided into clusters to create a tree-like structure like the one depicted here on the left, which is also called a dendrogram, to represent nested groupings of data points based on their similarity. The observation or any number of clusters can be selected by cutting the tree at certain levels. There are 2 main types of methods for creating this clustering. Agglomerative, which is bottom-up approach, is the most common approach. Start with each data point and on its own cluster At each step, merge the two closest clusters based on the distance metric, like Euclidean distance, and then repeat this until all points are merged into a single cluster. The other is called divisive, and this is less common. Start with all the data in one cluster and recursively split cluster until each point is in its own cluster. Density-based clustering. In these methods, we try to connect the highly dense areas into clusters. Doesn't require specific numbers of clusters in advance. This algorithm does it by defining a cluster as a dense regions of point separating by areas of lower point densities. The clusters are formed by connecting core points that are density reachable. That means that they can be linked through change of nearby core points. These algorithms can face difficulty in clustering the data points if the dataset has varying densities and high dimensions. Now we have an algorithm that we want to train our models, but now how do we know that our model performed well? So we're going to perform some evaluation. So model evaluation is iterative, and development of a model is an interactive process because of that. The model evaluation helps us to tune the model hyperparameters, also help us deciding if we need to add new features to our model or not, and importantly, it gives us some numerical measure or metric of model effectiveness to rank and select the model to be deployed. As explained before, depending on the type of method, whether it's regression or classification, the different types of evaluation metrics that we can use. For regression, R-square or coefficient of determination is one of the metrics which measures the proportion of variance in dependent variable, which is explained by the independent variable. Basically, the value of R-square is a value between 0 and 1 that measures how well our regression line fits our data. The closer R-square is to 1, the better our model will be at predicting our dependent variable. The top formula here is the residual of the R-square. The top part is the residual sum of square errors of our regression model. So that means that if the actual y value was 5, but we have predicted 6, then the residual square error would be 1. And then we would add this to the rest of the residual square errors for the model. The bottom part of the formula is the total sum of square errors. This is comparing the actual y value to our baseline model, the mean. And then we do this for all the values. The mean square error calculates the average of square of errors or deviation between the actual values and the predicted values. And the lower, in this case, the lower, the better. For classification, the confusion matrix is one of the most popular ways to evaluate a binary classification as well as multi-classification model. It is created by comparing the predicted class label of a data point to the true labels. And it is repeated for the whole dataset, and the comparison results are compiled in a matrix like this and can be used to calculate several metrics that are useful measures of model performance. So just to understand the vocabulary here, if we have a graphical view on the right, where we have in the rectangle on the left has the relevant element. That means all our positives from the true labels. On the right square, the true negatives from our labeled samples. And then we have within this circle, we have what has been predicted as relevant by the model. So in this set, we may have things that are true positives, so things that are predicted as relevant or positive, and they are actually labeled as such. We may have some data points that are predicted as positives, but they truly belong to the negative in the label categories. So these will be false positives, and we will put the number here. Then we will have those data points that are true positives, but our method did not detect them or retrieve them as relevant, or classify them as relevant. So we will consider these false negative. And then we have the true negatives, the ones that are negative and our system did not retrieve them or predict them as positive. The confusion matrix provides the basis for calculating the most widely used performance metrics. Let's start with precision, also called positive predictive value. It is defined as the number of predictions that are actually correct or relevant out of all predictions based on the positive class. So it are the true positives over the true positive plus false positives. These are the positives that have been predicted but are not. And if we don't have false positives, the precision will be 1. Here is the graphical view based on the graph here. Is the number of true positive predicted over all the positives, which includes true plus false. Recall, on the other hand, is also known as sensitivity, is a measure to identify the percentage of relevant data points. It's defined as the number of instances of the positive class, the true positives, that were correctly predicted. This will be over the true positive plus the false negative. This matrix is used when we want to catch the most number of instances of a particular class, even when it might increase the false positives. Here we have the graphical depiction based on our graph here. We're trying to capture the fraction of true positive versus the full set of positives. How many of the grand true positive we actually predicted. F1 score is the harmonic mean of precision and recall. It helps us to optimize classifiers for balancing both metrics. Accuracy is defined as the overall accuracy of proportion of correct predictions of the model. Normally used when our classes are almost balanced and correct predictions of those classes are equally important. The receiver operating characteristic curve is a visual representation of the model performance across all different thresholds. It's good for scoring classifiers, as it returns a probability value or score for each class label. The ROC curve plots the true positive rate, which we indicated is called sensitivity or recall, versus the false positive rate at various thresholds. The false positive rate is also known as false alarm, determining the total number of incorrect positive predictions among all negative samples. Ideally, the best prediction will be a point on the top left corner, indicating perfect classification, with 0 false positive rate and 1 recall. The diagonal line depicts a classifier that does a random guess. The area under the curve, which is AUC, but the curve we are talking about is the ROC curve, quantifies the overall ability of the model to distinguish between classes in classification and give us a numerical value to compare models. It represents the probability that the model, if given a randomly chosen positive and negative example, will rank the positive higher than the negative. The perfect classifier will give an area under the curve equal to 1. Based on this value, we can say that the higher the AUC score would be a better one. So thus the ROC curve helps us visualize how well the binary classifier can separate positive and negative classes by plotting true positive rate versus false positive rate across thresholds. But AUC summarizes the model's overall discrimination power. In terms of evaluating clustering models, which are a type of unsupervised learning, we use two metrics, internal metrics and external metrics. Internal metrics are used to evaluate the quality of clustering without reference to external data. They measure the cohesion within clusters and the separation between them. So we looked at how compact the clusters are and how well separated they are. These are internal metrics that solely rely on the data. On the other hand, the external metrics or validation validates the clustering model when we have some ground truth available as label data. And in that case, we have three measures or general metrics that can be used. One is called homogeneity. A clustering results satisfy homogeneity if each cluster contains only data points from a single class. In this case, this cluster contains all points that are from a single class. Basically, we are asking ourselves, are the cluster pure? This is disregarding whether other of these data types are in a different cluster. Completeness, on the other hand, is satisfied if all data points that belong to a given class are assigned to the same cluster. So in this case, all the triangles are in the triangle label class, are in a single cluster, even though there are some circles that ended up in this cluster. So basically what we are trying to respond here are all the members of a class together, which will be yes for the triangles and no for the circles. The V measure is similar to the F1 score in the sense that it is the harmonic mean of homogeneity and completeness scores, and it ranges from 0 to 1, and usually higher values are better. Here are the reference for this lecture. Thank you.